So hopefully you're starting to notice that we're getting a little bit more excited here. Why are we so excited about the while command? Well, in our field it's all about getting high performance. And in order to get high performance you want to use loop-based algorithms, in other words while loops or for loops, because that inherently allows you to control how you march through matrices, and how you march through matrices allows you to control how you use the caches, and how you use the caches allows you to control how much memory movement there is, and how much memory movement there is all has to do with whether or not you can get high performance, because memory movement represents overhead that gets in the way of high performance. And you will see a lot of that in week 6. So while loops is what it's all about for us, and we're finally getting to the point where we know how to prove while loops correct. And our tool here is going to be the while theorem. Now what's the while theorem? The while theorem, much like the if theorem, is a checklist that you can use to check whether a loop is correct. And we've been building up to this by talking about the loop invariant, where the loop invariant must be true, and how the loop invariant really allows you to use the principle of mathematical induction to reason about that loop. So what's the while theorem? Well, on the left you have a prototypical while loop that we have now annotated with a precondition Q, a postcondition R, and a loop invariant P sub inv. Hopefully you'll realize that the INV stands for invariant. And then we have a loop guard G. And in the previous unit we've already reasoned through how Q must imply the loop invariant, because you want the loop invariant to be true before the loop starts. That's the base case for our mathematical induction. And then we talked about how you should be able to reason that the fact that the loop invariant holds and G holds before statement S will again put you in a state where the loop invariant is true. That's the inductive step. You can then deduce through mathematical induction that the loop invariant holds before and after the execution of S every time through the loop. And then finally, if you come out of the loop, then you know that the loop guard is false, and if the loop invariant together with the loop guard being false implies R, then you know that the Hoare triple Q while loop R is actually correct, holds in other words. And that is what is summarized on the right here. The checklist is: check that Q implies the loop invariant, check that the Hoare triple loop invariant NG S, leaving you in a state where the loop invariant is true, holds, and check that the loop invariant together with the loop guard being false implies R. Now once you have proven that, all you really have is partial correctness, because it's only if you come out of the loop that you will have computed the correct result. And what you then still need to prove is that the loop actually at some point will terminate. And that's the topic of the next unit. In a lot of our algorithms we're going to have an initialization step, S sub I, and then the theorem changes slightly. Then you want to prove that Q implies the weakest precondition of the initialization command, leaving you in a state where the loop invariant holds. So back to our example. What did you prove in some homework exercise? Well, you proved that 0 less than or equal to n, together with the assignments 0 to S and 0 to K, leaves you in a state where the loop invariant is true. And how did we prove that? Well, this is what you need to prove. You instantiate the initialization command and the loop invariant. You then do textual substitution according to the definition of assignment twice, and that leaves you in this state. Then you want to sum over the empty range, which tells you that 0 is equal to 0, which of course just is true, so you can do n simplification, and then you end up with the precondition 0 less than or equal to n having to imply 0 less than or equal to n, and that's obviously true through another simplification step. So that's the first thing you need to compute. So then you have to prove that if the loop invariant and the guard hold before the command S is executed, then the loop invariant holds again after the command S is executed. And how do you do that? Well, you just kind of plot through it. This is what you need to prove. You instantiate. Notice that we don't instantiate to the left of the assignment because we're going to do a lot of manipulation on the right first. We then do the textual substitution of k plus 1 in for k everywhere it occurs. We then do a textual substitution of s, replacing it with s plus b of k. We then recognize that we probably should split off the last term of the quantifier on the right, so you get that. Then you can cancel b of k on both sides and you get this. Then you notice that s equals the same quantifier on the left as on the right, and all you're left with is to wonder whether 0 less than or equal to k less than n implies minus 1 less than or equal to k less than n. And if you want to do that formally, then you split minus 1 less than or equal to k less than n into minus 1 equals k, or 0 less than or equal to k less than n, because that then gives you exactly what's on the left hand side of the assignment. And then you can do n distributivity and weakening strengthening. And actually after this video we're going to have a small exercise that helps you reason through the fact that this then results in true. So then you're left with, is it the case that if you come out of the loop where the loop invariant now is true and the guard is false, is it the case that that implies that you've computed the correct thing? So this is what we want to prove. We can instantiate that. Notice that now we wait with instantiating R. We do some algebra where we notice that not k less than n means k is greater than or equal to n. And now we have that k is less than or equal to n and k is greater than or equal to n. So we conclude that then k is equal to n. We now instantiate R. And notice that what's on the left is almost what's on the right, except on the left the range goes up to k. On the right the range goes up to n, but we know that k is equal to n, so we can substitute that in on the left. And then we notice that we have something that we can apply weakening strengthening to conclude that this is true. Just like we had a worksheet for checking whether the if command is correct, we can now create a worksheet for checking whether a while loop is correct, at least whether it's correct if we know that the loop actually terminates. And in the next unit we're going to talk about how we determine that a loop actually does terminate.